All right, for this lesson, we're going to be talking about a couple of different topics. The first one is the concept of continuity. And what we're going to be looking at is continuity at a point on an open interval. So if you would take a second, look at the three images that I have drawn for you here. The first one on the left, if you notice, I have an open interval, the interval A to B, and it's open, not included. And then there is some point C between A and B. If you notice, just by looking on the interval from A to B, that function is definitely not continuous. Obviously, you can see there's a hole right there in the function. Specifically, the reason why it's not continuous is because f of c, in other words, the function value of c, is not defined. There's a hole there. So this is an example of something that's discontinuous, where f of c is not defined. The middle picture, if you notice, it's still an open interval from A to B. C is some point between the interval A to B. If you notice, this picture is not continuous either, and the reason is because if you notice, it jumps from one value to another. It's called a jump discontinuity. But more specifically, we're saying that the limit of f of x as x approaches c does not exist. Remember, in order for the limit to exist at that point, it has to be approaching the same thing on either side. So this limit does not exist as x approaches c. And then for the final one, you notice that this picture is also not continuous. There is a hole there. Now you're probably thinking, well, what's this little dot right here have to do with anything? Well, this dot lets me know that my function is defined at c. It's this value. So f of c is defined. Even more so, the limit as you approach c of your function exists because if you notice, it's approaching the same thing on the left and the right. But however, you can clearly see this is not continuous. The reason is because the limit, even though it does exist, and the function is defined, even though it is defined, they aren't the same thing. In order for function to be continuous at a point, three things have to occur. The first thing is your function has to be defined at that point. In other words, there better be a solid circle, a solid point somewhere. That was not the case here. The function was not defined at C. There's a hole there. So in order for it to be continuous, the first thing is the function's got to be defined at C. The second thing is the limit has to exist as you approach C. That did not happen here. So here's the thing. Here's the kicker. Even though the limit does exist here, this was not continuous because the function was not defined. Over here, function was defined, but the limit did not exist, so this was not continuous either. And finally, even if the function is defined and even if the limit exists, they have to equal each other. And that's why this one did not pass, was because even though the function is defined, and even though the limit does exist, the function is not defined where the limit exists. In order for it to be continuous, the open interval from A to B, some point C, the function would have to be defined at that point, and the limit would have to exist. And wherever function is defined, the limit has to be equal to that also. So you can see, out of all four of these images, this is the only one that is truly continuous, and it's the only one that matches all three of those conditions. And so that's what we talk about when we talk about continuity. Is that right there. All right, moving on, let's talk about continuity of each of these functions. Well, if you look at the first one, f of x is equal to 1 over x, clearly you can see that the function is not continuous. Specifically, right here, let me change colors, right here at x is equal to 0. It's definitely not continuous at x is equal to 0. In fact, you could even also say there's a vertical asymptote at x is equal to 0, but definitely not continuous. The domain of f is all non-zero real numbers, and you can conclude that f it's continuous at every x value in its domain, at x equal to 0, f has a non-removable discontinuity. And so, in other words, there's no way to find f of 0 so as to make the function continuous at x equals 0. So, in other words, the function is undefined at x equals 0, and there's a vertical asymptote there. So that's definitely not continuous at x equals 0. For this middle one, it's not continuous because there is what we call a hole, or more specifically, a removable discontinuity. And it is at x is equal to 1, right there, at x is equal to 1. There's a removable discontinuity there. In other words, the function g of x is not defined at x is equal to 1. And even though the limit exists, in fact, the limit as you approach 1 is 2, clearly, still not continuous. Number 3 is the only one that is continuous for basically the entire function. Sine of x is a repetitive, it's a periodic function. It ranges from positive 1 to negative 1. It just oscillates between those two values. There's no holes, there's no gaps. Definitely continuous for the entire domain. All right, keep on going. Continuity on a closed interval. This is very straightforward. So if you have a closed interval from A to B, closed interval means that those n values are included. A function f is continuous on the closed interval AB if it's continuous on the open interval AB. So in other words, there's no holes, no gaps anywhere between A and B. And the limit of f of x as you approach A from the right-hand side is equal to f of a, in other words, solid, right there. And the limit as you approach b from the left-hand side is equal to f of b. And if those three conditions are met, then there is continuity on a closed interval as well. Find the constant a such that the function is continuous on the entire line. Well, so I have this piecewise function. The top part says x squared minus c for x is less than 3, and 4x plus 2x for x is greater than or equal to 3. So it's a piecewise function. There's two pieces of this function. In order for a function to be continuous, three things have to be met. The function has to be defined, the limit has to exist, and then wherever the limit is, that's where the function is defined. So in other words, these two pieces better equal to each other. Because remember, the limit has to, the only way the limit can exist is if the limit is approaching the same thing on the left side as on the right side. And so the only place where we have to worry about being in discontinuity is specifically at the number 3, at x is equal to 3. That's the question. Is there a jump there, or is it a smooth, are they equal? So the best thing to do here is simply take our two pieces and set them equal to each other, because in order for them to be continuous, those two sides have to equal each other at that point, specifically at x is equal to 3. So the next step would be simply to plug in 3 for x. And so I'd get 9 minus c is equal to 12 plus 2c. And then you can quickly solve this for c by subtracting 9. You get negative 3. And then by adding c, you get 3c. And then dividing c, you get negative 1. So in order for this function to be continuous, I can go ahead and tell you that c has to be a negative 1 in order for this to be continuous. And so this would actually be the true function in order for it to be continuous. And if you plug in 3, you notice you get 9 plus 1 is 10. If you plug in 3, you'll get 12 minus 2 is 10. So the limit as you approach 3 on either side is approaching 10. The function is defined because right here is the inclusion symbol. And if you plug in 3 here, you get 10. And so the limit equals where it's defined. Everything works out. But the main thing is just recognizing that in order for it to be continuous, the left side limit has to equal the right side limit. So just set them equal to each other, evaluate it at the given point, at the given change right here, which in this case was 3, and then you can solve for c and go from there. Now, one very important thing about continuity is something called the intermediate value theorem. And it's a very self-evident theorem if you understand its premise. So it says if f is continuous on the closed interval a to b, so notice there's no holes or gaps on this interval a to b, it's closed, so from a to b it's closed, and k is any number is right here, between f of a and f of b. So in other words, k is a y value. There's at least one number c in that interval from a to b such that f of c is equal to k. In other words, there's no missing gaps. If there's a number that's between a and b, then it has to be equal to some number that's between f of a and f of b. It has to happen. It's just like if you were saying that you went from 30 miles per hour on the highway and you went to 60 miles per hour. If you were speeding up, then people are not going to say, well, you magically didn't pass through 55 miles per hour. No, 55 miles per hour is somewhere between 30 and 60. So if you went from 30 to 60, you had to be going 55 miles per hour at some point between that time. So that's what the intermediate value theorem is. Now, we can apply it to a problem that looks like this. It says, use the intermediate value theorem to show that the polynomial function f of x is equal to x cubed plus 2x minus 1 has a 0. In other words, this function is equal to 0 on the interval 0 to 1. Well, the first thing we got to do is we got to say, hey, is this a continuous function on the interval from 0 to 1? And it is. It's a polynomial function, so it's definitely continuous. There's no holes or no gaps, so it's definitely works. So let me just go back to it. So it's got to be continuous on the closed interval a to b, and k is any number between f of a and f of b. So we don't really know what f of 0 and f of 1 are. We can find those out by simply evaluating them. So f of 0 would be 0 cubed plus 2 times 0 minus 1, so that would end up being negative 1. And then f of 1 would be 1 cubed plus 2 times 1 minus 1, so that would be 1 plus 2 is 3 minus 1, that would be 2. So if you can envision this, the interval is from 0 to 1. That's the interval from 0 to 1. F of 0 is at negative 1. So f of 0 is at negative 1. So there's f of 0, it's negative 1. F of 1 is at 2. And we already said it's continuous, so it's going to exist everywhere between there. The intermediate value theorem guarantees, since it's continuous on the closed interval, 0 to 1, then this function has to have a 0. Well, why? Because isn't 0 between negative 1 and 2? It is. It's somewhere there. 0 is between negative 1 and 2. So that means at some point, this function is going to hit 0 somewhere between 0 and 1. Now, the intermediate value theorem doesn't specifically tell you how to find what that x-coordinate is. It guarantees that it does exist, and that's what's very powerful about it. So, yes, by the intermediate value theorem, I know that this function is equal to 0 somewhere between 0 and 1, because 0 is between negative 1 and 2. So somewhere between 0 and 1, this function is going to hit equal to 0. And we're not going to actually solve for that. You learned in pre-calculus how you could solve for that. You would literally say x cubed plus 2x plus 1 is equal to 0. You would solve this. And, you know, it might not take but a second. Maybe we could try out one little synthetic division, 1, 0, 2, negative 1. Let's see if this works. I'm not saying it will. 1, 1, 3. Nope, that one didn't work because I got a remainder of 2, so that didn't work. What about negative 1? I was curious. 1, 0, 2, negative 1. All right, so 1, negative 1, negative 1, 1, 3, negative 1. Oh, well, I don't know why I'm testing 1 and negative 1. It's got to be a number that's between 0 and 1. So, right, so I have no idea. I guess I could just graph it, x cubed plus 2x minus 1. In fact, why don't we do that? X cubed minus 2x plus 1, x cubed minus 2x plus 1. X cubed, I'm trying to remember it. I guess I can pull it up on here if I need to, and you can probably just pause or move on while it's setting up. I went ahead and took the liberty of graphing that function. So there's the graph of the function x cubed plus 2x minus 1. And if you notice, it does have a 0. And I can find that specifically, analyze, trace, graph trace, and then yep, there's the 0 right there. And look at that. The value of that 0 is 0.453, which 0.453 is between 1 and 0. But again, the intermediate value theorem doesn't find that answer for you. You still have to find it using different methods you've learned in pre-calc. What the intermediate value theorem is it guarantees if those conditions are met, then there exists some value between that an interval where the function is going to equal that value. And that's it for today's lesson.